We're going to jump ahead a little bit to this section just to kind of get away from all the algebra. This one's going to be a little trickier because this section is mathematical induction, and you usually use induction to prove things. The same way we're proving identities, right? The idea is you start on one side and you have to get to the right hand side by just using one side of manipulation. But the manipulation is a little different here. So we have to recall, before we get into it, we have to recall sequences. Hopefully remember what a sequence is. And we have to recall what a series is. And then a little bit of partial sums. Now, we don't have to know how to do them. We just have to be able to recall them to help us to understand what's happening in the problem. And I'll go through this quickly as I can. So, really quick. So a sequence is it's really just a collection of objects. But since this is a math class, the objects are numbers. But there's notation for these numbers, right? So we can have a sub 1, a sub 2, a sub 3, dot, 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 a sub n. Because this is just the dot, just assuming you continue. And now the reason why we use subscripts is just because we don't know how long this sequence is going. And using A, B, C, D, using the alphabet, there's only 26 letters in the alphabet. But with subscripts, there's an infinite amount of numbers. And now each one of these, we call them a term. So it's the first term, second term in the sequence. This last one, we usually call this one the nth term. Let me write that a little nicer. Nth term. Now, what does the nth term do? Now, something you might have learned before is usually what you learned in math is learning how to find a pattern in the sequence. And that's not saying every single number has a pattern, right? But usually you can have a pattern. So for example, i.e., let's say 1, 3, 5, and so on and so forth, right? Or here, I'll do one more. 1, 3, 5, 7. And you could probably assume what that pattern is going to be, right? But the nth term, right, that a sub n is 2n minus 1. And the idea is, I know that the next number is 9, and then after that would be 11, and then 12, because this is just all the odd numbers. Now, what is this doing? This little formula can help me find every single number in this sequence, right? And the idea is, if I plug in 1 for the first term in the sequence, I will get this exact number. Right, for example, if I plug in 1, right, that's going to be 2n minus 1 is going to be equal to 2 minus 1 is equal to 1. And then we can even do, let's say we want to find 7. That's the fourth term in the sequence. So it would be 2 times, or I'll write it out like a sub 4 for the fourth term. 2 times 4 minus 1 is going to give me 2 times 4 is 8, minus 1 is 7. So this formula here, this nth term, instead of me writing every single one out, let's say if I wanted to know what the 10th term was in this sequence, right? This is 1, 2, 3, oh, sorry, 1, 2, 3, 4. If I wanted the 10th one, instead of me going 7, 11, 13, 15, I could just plug 10 into this formula and it will give me the 10th term in the sequence. And that's something that you learn either in high school or another algebra, intermediate algebra course. Like learning to find those patterns. Luckily, we're not trying to find the pattern in this class. We're trying to just prove that the pattern that we found is true. Now, we assume this is true because I can tell, okay, it seems like every single number is going to be odd. But in math, you never want to assume something is true. You want to prove that it's true. So the idea is, how do I know the next one is going to be 9? Right? One, I just know it by numbers. And the next one's going to be 11. And the next one's going to be 13. But what if I do this like 1,000 times? How do I know that very next one is actually there? Right? How do I know it's going to be odd? What if just randomly out of nowhere it changes? Right? So in math, you usually, if I'm trying to prove the next one, and that's kind of what induction is, right? Is using the information I have to prove that the next one is true. And we usually use like an arbitrary number to do so. And that's a little bit of what we're going to be doing here. And the way to note the next one, so make a quick note. To emphasize the next one is a sub n plus 1. So a sub n is the term in the sequence. A sub n plus 1 is the way we emphasize the one after the one in question. Right? And this is an arbitrary way of stating that. Right? We're stating that n plus 1 term, which is the one that follows after. Because if I can show the one that follows after arbitrarily, and when I say arbitrary, just at random, there's no, I'm not checking a specific one. I'm just assuming if you're at 1,000, we're proving 1,001. If you're at 1,000,000,000, we're showing the 1,000,000,001, like the one that follows after. And just think about saying n plus 1 is just the general term of saying the next one. Right? I know the next one will also work. Now, that's just a sequence, right? In this class, we're trying to actually prove a different pattern. We're actually trying to prove the partial sum pattern, right? But partial sum, we first then have to then go back and talk about a series. So a series just means when you take that sequence and you start adding them together. Oops. I keep putting the parentheses, sorry. Dot, plus, and then 2n minus 1, right? That's the same thing. I just took every single term in the sequence and I'm adding them together. That's all a series is. Now, there's different notation for a series. For example, a series is denoted, I'm not going to go super into it, but the notation for a series is this capital sigma. That is just emphasizing summing. And then there's usually, you normally would write like I sub 1 and then n. So this is where you start, this is where you end. And then when you get into, for example, calculus 2, there's even infinite sums. Like, what if I add things forever? Now, when I'm adding these numbers, obviously they're getting larger and larger and larger and larger. But something that you also learn in an algebra course is this idea of partial sums. And the word it's already implying what this means. Partial means a part, not the whole. So we're adding not every single number in this series. I'm only looking for different parts. Now, for example, if I just look at 1, that would be the number 1. And then I can add, so let me see if I can note this. Let's say if the first one is just 1. But let's say if I want to add 1 with 3, right? That's going to give me 4. And then I want to add 1, 3, and 5. That's going to give me, right? 1 plus 3 is 4, plus 5 is 9. And then let's say we want to add 1 plus 3 plus 4 plus 7. That's going to be, so essentially 9 plus 7 will give us 16. And so on and so forth. So what's happening here is I'm showing that the partial sums has a sequence. There's this pattern in the way things sum, right? And the pattern is actually n squared. Because if you notice, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So again, we have a sequence. A series is take that sequence and add each term together, right? But there's a formula to find each term in that sequence. A series adds all those terms together. Our partial sum creates a formula to be able to find each one of those partial sums. So either adding the first one, adding the first 2, adding the first 3, adding the first 4. There is a formula. The same way here, we had a formula to find each term in the sequence. Well, this formula finds each term in this sequence, but this sequence comes from the series because the sums themselves are creating a sequence. And this is what we're trying to prove. We're trying to prove that this is true. Doesn't matter how many you want to add, the first 2, the first 3, the first 100, the first 1,000. I don't have to sit there and try to add like I was doing. I could just use this formula, plug in 1, I get the first one. I plug in 2, I get the second one. Plug in 3, get a third one. Plug in 4, get the fourth one. I can plug in 10. And that'll be the 10th term. It'll be the sum of the first 10 terms. And that's what we're trying to prove. And there's a process to this. And the process is here, where for each natural number n, so what this first line is saying, well, for example, we're saying the first term, second, third, fourth. So if you notice, I'm counting natural numbers. I'm not saying the 1.5 term, the 1.231 term, right? Hence, this n that we're talking about is a natural number. So think about all the positive whole numbers is essentially what a natural number is. And then we let P of n be the statement depending on n. So P of n is this formula here, right? This is a formula that gives me the sum of this series, partial sum. Now, how do I know this is going to always work forever? So the idea is we suppose that the following 2 conditions are satisfied. So the goal is for me to show that this always works. I need to satisfy the next 2 conditions. And it's almost like 3, right? The first thing you do is check the very first term, right? Because if this formula doesn't even give you the first term, then there's no point in trying to prove it. You have already showed that it doesn't work, right? That's usually a way to disprove something, is to find at least one situation where it doesn't work, right? Some of us sometimes find little techniques, little ways of solving problems our own way. But maybe you've had an experience where a teacher then used a specific number or a specific situation where what you thought would work then failed, right? And that's because that's the natural way, like we were taught to disprove something. To disprove a formula or a method or a definition, you just need to find one situation that it fails and you've disproved it. So this is us checking one, because if it doesn't even work for one, what's the point in checking all the other ones? So then the second thing is we actually assume this part. So we check here, right? This first step is we check. And then this second line here, this is what we assume. Oh, sorry, not here. This part. This part here is if P of K is true, right? So now we're choosing a different, like this is the N in question. I'm going to choose K, which is, you can think about it, a subset of N. Because we can check 1, we can check 2, we can check 3, we can check 4, we can check all the way to 100, right? That's essentially what this K is doing. It's checking up to 100. If P of K is, so this is a part we assume, right? We assume this part. Because the idea is we check the first one, and we're assuming that K is true, meaning I know this is working all the time, right? I just checked it. I can check first, second, third, fourth, fifth. At this point, I'm pretty confident that's going to work for every other term that follows, every partial sum that follows. But I need to prove that, right? So if the first one works, and then I assume every other number that should work, then that means, remember, that K plus 1 means the next one should work. So that covers all our bases. The first one's working, every other number after that should work. And we're even saying that if you check to some crazy number, even the one after that is also going to work. Like it's going to work forever. And that's kind of the setup. Even though it says 2 conditions, it really feels like, to me, like we're breaking it down to show 1, assume everything is working, and then we have to show that the next one is going to work. And if we can complete this, then we have proven that this is always going to work forever. So let's break it down. Since we were just talking about this one, let's actually start with this. So how are we going to prove this? Let's start with, here's our proof, right? Let's start with, like I said, we call this the base case. So the base case is checking the first one works, checking P sub 1. So that means I'm going to plug in 1 here, and I'm hoping to get that very first term. Not this one. This is not what I'm trying to prove. I'm trying to prove this side, right? That this does equal that N squared. So that means I check it, I plug in 1. So let me use some colors here so it helps to understand what I'm doing, right? 1. And then let me change the color of this to purple. Or, no, not purple. Let's use green. Just so I can show that. I don't know if this is getting too colorful, but hopefully you see that I plugged into that N squared, and that gave me no, this doesn't make sense. Sorry. There's too many colors. But the idea is we do get 1 from plugging 1 in. Okay, that feels better. So the idea is I'm just checking my first term. I plugged in my first term, And this, so this one is not this one. It's just hard to show it because the first term is the number 1. So I plug in 1 and I square it, and then it gives me that first term. So here it checks. I'll do another example where it's going to make a little bit more sense, the checking. But the idea is this one means the first term. This one is the actual number in the first term. So we checked our base case. Now we have to do our assumption. Right? So this is like step 1. And then our step 2 is we have to assume P of K is true. But what does that mean? What does it mean for P of K to be true? So I'm going to say that is, meaning I'm going to display or show you what does it mean for this to be true. And for P of K to be true, I'm saying that we get 1 plus 3 plus 5 plus... Remember, this is the part where I'm saying we're just checking that the sequence does work. So far, 2k minus 1 squared. And this is kind of silly because we're just literally writing this everything out, but in terms of k. But right, the idea is that k is sort of a subset of this n. So this n is representing forever. This is something finite, like something that we can actually check. Like we check to 100 or 1,000, and that works. So I check the base case. I assume the P of K term. Now we have to show. Then, so I'll put a period here. Then we must show that P of K plus 1 is true. Right, that's the idea of what we're doing. But what does it mean so we must show P of K plus 1 is true. So that's showing that the next one is going to work, right? That's this part where it asks us, then P of K is true. But we have to show that. That's a conditional statement, right? And the condition is 1 needs to be true for the second one to exist, right? For example, if it's midnight, then it's dark outside. But first, I need to satisfy the midnight part for me to know it's dark outside. But it's not true the other way, right? Just because it's dark does not mean it's midnight. That would be, if that was true, that would be a biconditional statement. But this is a conditional statement. So we're starting with the first part we know is true. I have to show this next one. Now, something I like doing, just because it helps me visualize like what my end goal is that I just plug K plus 1 into my formula here to what I'm trying to show, right? And the reason for that is and I have an idea of what my end should look like. So what does that mean? So that means I have to take this 1 plus 3 plus 5 plus ... plus k minus 1 squared. And I'm going to include that next one. Because I need to show P of K does end up giving me this k plus 1 squared. So I plug in k plus 1 on this left side, right? So I'm showing that the next term is going to work, hence this is working forever. But I have to show that it gives me this. So this is the idea. So I have 2 and then k plus 1 minus 1 squared, right? So again, I need to show k plus 1, but I'm going to show that they end up giving me this value. But I'm only going to work with the left-hand side to produce the right. Because if I'm showing that this is working, then the next one works. And I can show that this formula is still going to give me the same representation with k plus 1 in it, then it must work forever. I know it's a little confusing, but think of the idea of like being that next one. Now, if you look here, right, this is exactly what I already assumed here. So I know all of this is equal to k squared, right? This whole thing here is k squared. And then I am going to add that with this next portion, right? If I distribute, oh, I made a small mistake. I don't know if you guys caught it. There is no square here. I have no idea why I'm adding a square. There's no square there, here, or here. I apologize for that. I think I kept looking at this square and I added it in. I'm trying to show this square, but there is no squaring on this left-hand side. So sorry for that. But this is still true. And then here I can distribute that 2k. So it'll be 2k plus 2 minus 1, right? And then this is going to simplify to k squared plus 2k minus 1. And now this is where we start doing a couple different tricks. If you look here, this, let me change my colors. This here is a quadratic. So if you remember how to factor, this factors into k plus 1 times k plus 1, which I can then write as k plus 1 squared. And that's exactly what I was looking for, right? That was my goal, is can I show that that left-hand side becomes k plus 1? And if you notice, I never used this right-hand side to do that. I plugged in k plus 1 to show that the next term works, right? This is a sub n, and this is a sub n plus 1. So I added this extra term, and I was able to get as if it was k plus 1 squared. So because of this, we say thus. I'm going to kind of squeeze it in, thus. So I'm going to put a period there. Thus, I could probably have everything written down. So I'm just going to say thus, P of n is true for all natural numbers n. And then usually some people like to do this little box to kind of show that it's all true. Now let's jump right into another example to not make this super long. So here we go. Our next example. And maybe I'll make another video with a couple more examples. So once again, our base case. Let's do our base case, which is going to be P of 1. So again, this one, luckily that first term isn't 1. So 1 is just me saying the first term, and I'm going to plug in 1. 2 times 1 plus 1 is equal to essentially 2 plus 1, which gives me 3. And that is that first term. So I do get the first term, hence my base case checks, period. Then we have to do our assumption. So this is our second step. This is like the induction step, some people call it. So assume P of K is true. That is, what does it mean for P of K to be true? It's that we get 3 plus 7 plus 11 plus ... plus 4n minus 1. Oh, sorry. K will give us K times 2K plus 1. Then and then it just becomes like you follow. This just becomes very like algorithmic, step by step. We must show P of K plus 1. And this step, you don't have to show it, but I always like writing what does it look like for P of K plus 1 to be true, just because it helps me visualize what my end goal is going to be. So 2K plus 1 plus 1, right? So this is what I'm trying to show here. So the idea is I'm trying to show this. Now, so that means we're going to rewrite this, right? So we're going to show that 3 plus 7 plus 11 plus ... plus 4K minus 1 plus, and now we're going to do 4K plus 1 minus 1, and then that's going to equal, once again, this, you always do this step, this is equivalent to what we wrote, which is this K times 2K plus 1 plus, and now I just have to work this part out, which I can distribute, and that would give me 4K plus 4 minus 1, and that will simplify to, and if I were to distribute this portion, it's 2K squared plus K, and then I have plus 4K plus 3, right? Because 4 minus 1 is 3. Which, if you simplify, this is going to become, that's going to become 2K squared plus 5K plus 3. And then from here, you have to recognize that this factors into K plus 1 times 2K plus 3. Right, so it's kind of that same technique as before. And the idea is, last time, the factoring, was exactly what I wanted. Now I have the K plus 1 portion, but I don't have this second part yet. But we actually do. And that's this 2K plus 3. But how do I get that 2K plus 3? And this is where these problems, you have to get a little creative. So I write 2K plus 1, and then I have to write 2K plus 4 minus 1. Now, why do I do that? And I do that because, we can actually split it. Sorry, that's not it. Because look, I'm trying to get to this here. Now, sometimes what you can do is, since I already know what I'm looking for, sometimes I can start opening up. So if I make a quick note, I can take this, and then this is similar to what we did with with verifying identities, where sometimes I said, well, if you want, sometimes you can start working, even though you're not supposed to work with the right hand side. I sometimes do it to guide my thinking, right? To guide me in the right direction of like, okay, what do I do? Right? Like, how can I break this down? So that's going to be 2 plus 1. And if you notice, this 2 plus 1 becomes 2k plus 3, which is exactly what we have here. So me doing that shows me, again, I'm not saying, okay, cool, I'm done. It gives me a path to get back to what my goal was. So that actually tells me to write this as 2k plus 2 plus 1. Because that ultimately lets me write this as k plus 1 times 2 times k plus 1 plus 1. And now I have gotten exactly what my... You can even take a step further and show that this is actually equal to 2 k, equals the k plus 1, which is this portion that I was trying to get to. And since I got there, like I said, we follow that last final statement, and there's ways to finish it. We can say, therefore, therefore P of n is true for all natural numbers n, and we can just box it off. Now this is really where the problem becomes, where you have to try to find how we can manipulate it to get here. And this is a technique I sometimes follow, where I have like some side work that kind of guides my thinking. And just like with when I showed you verifying identities, right? If I go back, when we verified identities, right? Sometimes we have to think back to our algebra, right? Sometimes doing factoring, right? How does it work to add fractions together, right? We need the same denominator. So for these proofs, sometimes we do have to go back and rely on our algebra. But to not make this video super long, I will make another video showing 2 more examples, just because these are a little tricky, and I'll give you guys some practice. But that's the idea of these inductions, and I'll make more.